Okay, so let's get started with our pancreatic hormones and talking about treatment of diabetes. So the endocrine pancreas, as you no doubt recall from your physiology lectures, is composed of a number of different cell types, including those which are exocrine in nature. So the alpha cells that produce glucagon, that increases the breakdown of glycogen into glucose, primarily in the liver. Beta cells, which are responsible for the secretion of insulin and the increase in glucose uptake and utilization. And the delta cells, which secrete somatostatin, which inhibit insulin and glucagon release and have also additional effects outside of the regulation of glucose homeostasis. So our therapeutics here are all around diabetes, and so we have two types of diabetes. We have more than two types, but we have two major types of diabetes. Type 1, which is early life onset, typically autoimmune destruction of pancreatic beta cells. It may be juvenile in nature, so the baby may be born with type 1 diabetes or have very early onset as a toddler. Or you may acquire it, but typically it is below the age of 40 when you acquire type 1 diabetes. With the destruction of the beta cells, then there's loss of insulin and the requirement for replacement therapy. Type 1 diabetes is a part of a sort of whole array of autoimmune conditions. And so people who have other autoimmune diseases are often at higher risk for type 1 diabetes as well. Type 2 diabetes, on the other hand, has a typical later life onset associated with increase in body weight and obesity. There is insulin resistance in target tissues, and eventually there's a feedback and increases insulin secretion as a result of inappropriate stimulation of the insulin receptors. And there is eventual hypoglycemia and eventual involvement of the beta cells, and oftentimes a requirement for insulin therapy with advanced type 2 diabetes. So those of you who've taken my PCR302 class recently will be familiar with some of these slides, where you can see that the normal changes in serum glucose levels are relatively conservative as we take in our food if we are not a diabetic. So we have, with a rise in serum glucose, then we get excretion of insulin from the pancreas, and that rapidly then results in uptake of that glucose into stores and utilization of glucose if there's a requirement for that. In the non-diabetic, on the other hand, these serum glucose levels tend to swing a lot more wildly into the realm of hypoglycemia, where you often get these large spikes of glucose postprandially. That means after you've taken a meal. So on this graph, you can see that their food intake is here throughout the day. And in the case of the diabetic, who's taking on insulin a couple of times a day, then if they take in insulin, they will get control of their blood glucose and bring it back down again, but then it tends to rise again into the hypoglycemic range after lunch, and then that starts to come down, and then it rises again with supper. And then they take on board some more insulin at that point, and that will tend to bring it down again into the normal glycemic or even the hypoglycemic levels, depending on how well controlled they are. So our goal is really to try to mimic what you see physiologically, and so nowadays, very typically then, that multiple types of insulin are used in order to have different durations of action. Different onset of action and different durations of action. So our ultra-fast lec3-2 insulin then has an onset of action that is pretty rapid and will have a maximum effect about between half an hour and an hour, and those effects wane within 2 hours. Regular insulin has a little longer duration of action, intermediate, even longer, long-acting ultra-lente, and long-acting ultra-lente, and then glargine, which is ultra-long-acting, which will give you a background level of insulin secretion from a depot over 24 hours. So intensive insulin therapy, which was found to be really important for control of the longer-term effects of diabetes. So the long-term effects of having low glycemic control are numerous. And so we get a whole array of apathies. We have retinopathy, so diabetes is a leading cause of blindness. We have degradation in the kidney, which kidney failure is one of the major causes of kidney failure, and kidney disease is diabetes. We also get neuropathies, particularly peripheral neuropathies with diabetes, and so oftentimes there is insufficient circulation in the periphery, and so we will tend to get poor wound healing, and in response to that wound healing, or lack of wound healing, then oftentimes limbs become gangrenous and have to be removed. And so a large amount of limb removal is a result of diabetes, or complications of diabetes. So trials were done to see whether intensive insulin therapy would have a better crack at taking care of some of these long-term effects of diabetes. And indeed it did, and there were a number of studies that showed that intensive treatment with frequent monitoring of blood glucose, 3 or more daily injections of insulin and combinations of insulin were going to have some much better effects, much slower onset at least of some of these complications. So the patient has to be very well educated in terms of their taking on board their food, when to take, what types of foods to take on board, adjusting their insulin levels, and frequently monitoring their blood glucose levels, which is becoming more easily. So typically you would take a very fine needle and draw a small drop of blood, measure that on a glucometer, and nowadays you can have one attached to your arm, which allows you to monitor your blood glucose peripherally without having to draw blood. And so it's becoming a little less onerous, but nevertheless insulin has to be delivered by injection. So it still means poking yourself probably several times a day unless you're on an insulin pump. So what do we see? So with our regular diabetes protocol from years ago then, with a patient would typically take an injection of, say, Lispro insulin early on in combination with a longer acting insulin. So they would take that early, usually first thing in the morning before breakfast. You see the rise in insulin then with that early or the more rapid onset insulin and the lower onset insulin here. And then so their meals would be taken here at regular intervals. So with the more intensive intake, then the patient takes on board Lispro as opposed to regular insulin and glargine, and they take those again now not twice a day but 3 times a day in order for them to give better control, particularly of the food coming, the glucose coming downstream of the food. And there's the background long-acting insulin here. So I'm going through this fairly quickly because I'm assuming most of you have had some background in diabetes and regular therapies. If you haven't, and you have some more questions, certainly come to see me. So, as previously discussed, then, there are anti-hypoglycemic drugs, and so we previously discussed these in PCL302, that span the range of insulin secretagogues, insulin sensitizers, and inhibitors of carbohydrate absorption. And so these are an array of older drugs that have been on the market for prolonged periods of time. So our sulfonylureas and the newer repaglinide and ateglinide then are insulin secretagogues, and so they are going to increase the amount of insulin that is going to be released, and that will then help you to deal with the glucose that comes on board with your food. The biguanides and the glidazones, on the other hand, are insulin sensitizers, and they help to increase the responsiveness to insulin, which is decreased in the patient with type 2 diabetes. And then finally, the inhibitors of carbohydrate resorption, then, or absorption, I should say, are ones that are aiming to decrease the rate at which you see that spike in glucose in response to taking on board your food. And so they just slow down that carbohydrate absorption. So let's start back at our first sulfonylureas. And so their mechanisms of action and the drugs which are going to be regulating insulin secretion are working at the level of this ion channel here, this potassium channel, which is being regulated. Let's get on board here. Our signaling system. So what we normally see in the beta cell is that glucose is taken up through the GLUT2 transporter. And the GLUT2 transporter, then taking up that glucose, increases the level of ATP in the cell. ATP will inhibit this potassium channel, and when it inhibits this potassium channel, it closes, and that depolarizes the cell membrane. When it depolarizes the cell membrane, a voltage-gated calcium channel is opened up, and that change in membrane potential, and calcium then can move into the cell. And when it does, then that rise in intracellular calcium results in the release of insulin from the preformed insulin sitting in the granules in the beta cells. So that insulin then goes on and increases the amount of glucose uptake into the cells. So what the sulfonylureas do then is to regulate this potassium channel in such a way as to close the channel so it inhibits it, and essentially mimics what you see when you've taken on board the glucose into these cells, and you get the depolarization and the calcium and the increase in insulin secretion. The difference here is that under the physiological control, then this is being coupled to the levels of glucose in the blood, whereas when you're using sulfonylureas therapeutically, it is no longer coupled to the glucose levels in your blood. And so you can imagine that what can happen is that in response to sulfonylureas, is that you can get a state of hypoglycemia, which is not well matched to your food intake and the amount of glucose that is being produced. Now, the other ways in which we can treat type 2 diabetes is to sensitize our cells or to increase the cell sensitization to the actions of insulin. And we can do this with an old drug namely metformin. Metformin is very typically the first drug that you get given when you have type 2 diabetes. So its mechanism of action took a long time before we figured it out. We were using metformin for many decades, knowing what it was doing, but not really understanding its mechanism of action. So what it does is correct, in particular, hepatic glucose output. So one of the things that goes awry in type 2 diabetes is not only your insulin sensitivity, but the glucagon stimulation of glycogen breakdown. that you see, particularly from the liver. And that tends to be elevated in type 2 diabetes, so that even in the absence of you taking on board nutrients and glucose, you're getting glucose being released from the stools. So what metformin does is help to regulate that side of things in the liver. So it decreases insulin resistance. It's mediated through regulation of 5' AMP activated kinase, or AMPA kinase, in hepatocytes as well as in muscle, but its primary effects are really in the liver. And because it doesn't increase insulin secretion, but increases sensitivity to insulin, then you typically don't get hypoglycemic events in response to metformin. So it's a popular drug in that sense. You can take it, nothing really appears to be happening, but it helps to control your hyperglycemia without giving you the potential for hypoglycemic events. The other things which are sensitizers indirectly in some ways are the thiazolidine diones. And they act by stimulating the transcription factor PPAR gamma. And so PPAR gamma, which is a peroxisome proliferator activator receptor, and the gamma type of these PPARs, there's several PPARs. It's a nuclear hormone receptor, and it's expressed at high levels in adipose tissue. And so as a result of stimulation of PPAR gamma, you get increased differentiation of adipocytes. And so you will generally, when you take thiazolidine diones, you will typically gain extra fat. Now, because type 2 diabetes is associated with obesity, it seems counterintuitive that you want to give people a drug that will increase their obesity. Because generally what you're going to do is suggest that they decrease their food intake and increase their exercise in order to decrease their weight. But the rationale behind using glitazones is really to increase the amount of fat and the potential to store glucose out of the bloodstream in those fat stores. So the thing which is particularly cytotoxic is that hypoglycemia. So having that poor control of glycemia is the thing that's really, really bad. So people suggested then that increasing adipose tissue in order to increase storage of that extra glucose then would have some effect on those long-term effects, and indeed it does. So there are a number of different things which get changed. So TNF-alpha, which impairs interactions with insulin signaling, is decreased with PPAR gamma stimulators. Leptin, which is a hormone which should be signaling back to your brain to say that you've got enough food on board, because you've got leptin which is being produced from your adipocytes and therefore should be suppressing your appetite. That is often ignored by people, and we carry on eating even when we're not hungry. And I think probably all of us are guilty of doing that at some time or another. But leptin may interfere with insulin signaling, so that release of leptin can interfere with insulin sensitivity, and so its decrease in expression may help improve sensitivity. Lipoprotein lipase, which is involved in uptake of triglycerides by fat, there's increased expression of lipoprotein lipase, so that also helps in dealing with the extra triglycerides that are floating around in your blood typically when you're overweight, or even when you're not, oftentimes. And then GLUT4 and GLUT1 are increased in expression in response to PPAR gamma stimulation. So there are a number of very positive effects from the point of view of metabolic balance. But because of the fact that glitazones do increase fat, and they do also have pretty bad effects on bone, they tend to shift osteoblasts from their differentiation into adipocytes because they're all of mesenchymal origin, so are precursor cells for osteoblasts and muscle cells, so things which build bone and muscle, and our fibroblasts for our connective tissue are also the same origin as adipocytes. And so when we give glitazones, one of the things that we see is that those mesenchymal cells start to shunt towards adipocytes, which is what we're trying to do with these drugs, but they also tend to give you fatty bones, so they cause problems with your bone. So these drugs have gone a little bit out of fashion in terms of usage, I would say. Okay, so thinking a little bit about type 2 diabetes. So we do know that the levels of type 2 diabetes are getting to be absolutely out of control in almost all societies. The number of diabetics are in the multi-millions worldwide and probably heading towards 1 billion or more. So if we start to look in countries in the Western Hemisphere, so in Europe and the West, North America, we've had an awful lot of obesity for probably quite progressing, particularly since the 1940s and the 1950s. So before then, if you looked at your average American, they would have perhaps a bit of weight gain in their middle ages, but probably wasn't more than having a little bit of a belly on them, right? Nowadays, on the other hand, what we typically see is levels of obesity which are rampant, with a good 1/3 to 2/3 of the population, depending on what age group you're looking at, are into the obese category of having a BMI over 30. So we have clearly some problems with decreased energy expenditure and increased caloric intake. So these come under the level of environmental problems. Consider them to be environmental problems. They're obviously not under our own control, but they are environmental problems. So along with this, people have had a look at a number of different things. So what is it that's causing these problems? Well, one of them is the ready availability of pre-cooked, pre-formed foods with high caloric content, for which we have to do absolutely no work other than push a button, right? Usually on the microwave, and then we've got a couple of 100, if not 1,000 calories coming on board. We also tend to do things like drink large quantities of sugary liquids. So lots of people drink lots of carbonated beverages. Your average Starbucks macchiato contains enough calories in it to be should be a fairly satisfying meal, but we don't think of these things as meals, right? So we are surrounded constantly by all of these lovely, delicious foods that we can get access to relatively cheaply, relatively easily, with very, very little effort on our parts, right? When was the last time that you walked to the store, got the ingredients, walked back home, spent 3 hours producing your meal? Anybody want to put a hand up to that? Very good. Excellent. You've got some home cooks here who are doing those things. Great. I'm glad to hear it. So the majority of people didn't put up their hands, so they didn't do it. Maybe mom or dad did, but most of us tend to spend very little time preparing our food anymore, right? And so in addition to that, the dietary nutrients, how many nutrients and what types of nutrients we're taking in can be an issue. There are certainly issues around epigenetics, so looking for genetic causes of type 2 diabetes has not been horribly fruitful. There's a lot of associations have been shown for many different genes and changes in genes and epigenetic modification of gene expression. But there certainly is no one gene that's changed, and there's certainly not even a short list of things which are changed in type 2 diabetes. So it's clearly a very complex problem. And then there are issues around our microbiome. So we think about microbiome mainly in the gut. And so there's a lot of talk about microbiome and the contribution of the microbiome to all sorts of diseases, including inflammatory-based diseases such as diabetes, but lots of other things. And those have come about as a result of the fact that we're not eating the right assortment of microbes. We are doing things which oftentimes are not good, creating a good environment for the microbes in our gut that are very important for maintaining our health. So these are all sort of environmental factors that in a large number of people, in a growing number of people, result in obesity. Now that obesity then, so does obesity necessarily mean that you're going to end up with type 2 diabetes? No, not necessarily, but you certainly are at much higher risk of type 2 diabetes. And so those adiposity genes then, which have been stimulated remarkably, seem to be feeding onto our beta cells and creating some dysfunctional beta cells. And so the result of these two things together then often leads to type 2 diabetes. So these are some of the factors, and we don't really know a lot about all of them, but it is quite clear that access to lots of food and calories is certainly one way in which we have seen these problems. The other is clearly genetic. So if we look at some specialized populations, so the ones that people typically turn to are some of our native North American and Northern European populations who have evolved to survive in very harsh environments in which they don't have access to lots of foods for many parts of the year. But so they live on, or they used to live on, well, they have been hunting and fishing, and so they would eat foods which were highly enriched in fats, highly enriched in protein some parts of the year, but oftentimes were not highly enriched in carbohydrates. And so they have evolved to create lots of fat stores, and oftentimes went for prolonged periods of time, certainly over the winter months, where they did not have access to lots of foods. And so they would eat a very poor diet and live off their fat, as many animals do. Very similar. The trouble with that, as people have evolved to deal with those environmental problems, when they then find themselves in the face of much more readily available foods, and particularly high carbohydrate foods, that tends to result in a high propensity for increasing fat and type 2 diabetes. So the levels of obesity in those populations are often much higher than 50%. And the levels of diabetes, type 2 diabetes, are even higher. We also see rises of diabetes, for example, in countries where we're getting a higher proportion of people entering into the middle class with better access to food. So China and India are very good examples, and having huge populations in both of those countries, the numbers of diabetics are going absolutely through the roof in India and China. The highest number of diabetics right now is in India, and China is catching up, if not taking over. So they are likely to go through the whole storm that we went through in the Western world if they are not learning lessons. Okay, so thinking about some of the new therapeutic approaches. So in the GI tract then, pramlintide is an amylin analog, and it releases amylin, or it helps to, amylin is released from beta cells with insulin and helps slow gastric emptying. So this amylin analog is then going to be doing the same thing. So the idea here, again, is to decrease the rate of delivery of carbohydrates from our system in the form of glucose. Cholesevelam, God, they make these names difficult, is a bile acid binding resin that lowers cholesterol and modifies GI peptides and improves, once again, plasma glucose by decreasing those GI peptides or modifying those GI peptides. So these are two things which are being used somewhat to interact with the GI tract. The other ways in which we do it is to use drugs like azabos, which are alpha-glucosidase inhibitors, and decrease the delivery of glucose into the system. Now, GLP-1 and its uses in diabetes. So if we look at GLP-1, then it is being released from the epithelial L cells in the intestines. And what it does is to feed back to the level of the pancreas and increase pancreatic insulin production. It increases beta cell growth, so it's very important for promoting pancreatic health. And it also reduces resistance to insulin. And so it helps together then between these activities help to improve metabolic tolerance of glucose. And it also can feed back to the level of the brain and decrease appetite. So GLP-1 levels, which increase postprandially, then help to reduce type 2 diabetes or the symptoms of type 2 diabetes. There is a decrease in adenyl cyclase type 5 expression in type 2 diabetes. And because GLP-1 is linked to GS, its receptor is linked to GS and stimulates adenyl cyclase, the suppression of AC5 in type 2 diabetes may have some effects at the level of the pancreas. The other thing that we see at the level of the pancreas is alpha-2 adrenergic receptors. And you may recall that alpha-2 adrenergic receptors stimulate GI alpha and decrease the amount of cyclic AMP. And so they will have the opposite effects of GLP-1 in terms of its effect on insulin secretion. So our incretins and gliptins then are all around GLP-1 regulation. So incretins such as liraglutide is a GLP-1 receptor agonist. So if we're not getting appropriate levels of regulation through GLP-1 receptors, then maybe we can compensate that using agonists. So it increases glucose-stimulated insulin release from the beta cells, and this is important here that it's glucose-stimulated. So GLP-1 on its own is not going to increase insulin secretion, but it will help sensitize those beta cells to glucose levels. So it decreases glucagon secretion from the alpha cells, so it's a double effect then. And as I've said, because glucagon is dysregulated also in type 2 diabetes, GLP-1 then is having positive effects in terms of insulin and also having positive effects by decreasing the amount of glucagon that's released, which will then decrease the amount of release of glucose from glycogen stores. The other way in which we can regulate GLP-1 is through blocking its breakdown. So DPP-4, which is dipeptidyl peptidase 4, and its inhibitor, which is cetugliptin, is going to then help decrease the breakdown of GLP-1. So when we give PP4 inhibitors then, we can increase the amount of GLP-1, and that will again have very positive effects back at the level of the beta cells and the alpha cells. So we can either stimulate through the agonist or we can decrease its breakdown. The other thing that people find is that with DPP4 blockers is that it also regulates the levels of many other peptide hormones, not just GLP-1. And so it's finding, as people are starting to use this drug more often, finding that it's having positive effects on the cardiovascular system and helping to decrease hypertension, and remember that people with diabetes are at 5 times higher risk for cardiovascular disease, including heart attacks and strokes. So this is very often fatal in the case of a diabetic. So by blocking the degradation then of some of these peptide hormones, then they have vasodilatory effects, and that is helping with the cardiovascular complications of diabetes. So a triple effect then coming through these DPP-4 inhibitors, and they're starting to become very popular drugs for the treatment of type 2. Usually in combination with other drugs, so metformin, say, plus a DPP-1 inhibitor, or a gliptin. The other way in which we can regulate things is through sodium glucose transporter inhibition. So SGLT2 inhibitors block the reuptake of glucose from the nephron. And so with these inhibitors then, you get positive decreases in plasma glucose. And that also has translated into positive effects in terms of weight and blood pressure. So this helps then decrease the amount of glucose that we're going to get back into the system once we've already seen it passing through into the nephron. But the negative effects that we're seeing is a 5 times increase in myocardic infections in the urinary tract. So because we're increasing the amount of glucose which is being excreted in the urine, that urinary glucose then makes a very comfortable environment for the growth of myocardic infections. So we're getting a lot of fungal infections then in the urinary tract as a result of that. There's also some effects on LDL and HDL, and so far the cardiovascular consequences of using these types of drugs, which your example drugs are up here. I'm not even going to try at this point to pronounce them because my voice is going. Because we really don't know what the long-term cardiovascular effects are yet. So the other thing that I just wanted to close up with is some newer therapies which are coming around modifications of insulin. So some of these are available in the EU and not here yet, at least I don't think so. I don't have time to look this up, but I'm not too sure that degludec is yet available in North America. We have soluble hexamers of glucose with a half-life that's improved to give us better nocturnal control. So you may recall from your 302 lectures that one of the problems that diabetics typically have problems with is control of their nocturnal glucose, their overnight glucose. So they often wake up in the morning with very high glucose levels as a result of that. And so the potential then for having having insulins with very long half-lives then might improve that. The other way is that people are putting insulin on polyethylene glycol to potentially increase its half-life. And some inhalation formulas, as I said about insulin, much like you saw with the calcitonin, have been abandoned. And in the case of insulin, because of an increase in lung cancer, has been found with inhalation forms of insulin. And finally, there are some smart insulins which are being put together. And these are really interesting little things. So people said, okay, we want insulin, but we want insulin around at the right time. So what if we make some glycosylated insulins and bind them to lectins, and then they can circulate, and when your serum glucose levels go up, when your serum glucose levels go up, then they will compete with these glycosylated insulins for binding to those lectins. And therefore, then the insulins will be released from those circulating pools in response only to your serum glucose, which is pretty much what your normal physiology is doing. But this is a way of delivering it potentially in a more smart way from the point of view of trying to control your glucose levels. So these are not in use currently, but they're in development. And I think they're kind of interesting ideas that are coming along. The other thing that people are doing is to use progenitor cells to potentially increase new beta cells. So the production of new pancreatic beta cells then is one of the focuses for cell-based therapies that are not yet therapeutically used, but is hope for the future that we may be able to replace the pancreas, or at least the beta cells in the pancreas, and have normal glucose control of those beta cells. All right, so I think that pretty much wraps up today, and I'll see you Wednesday.